Oh, Professor.
Professor.
Oh, I'm sorry about that. So he's arguably one of the broadest young theorists in high energy theory. He worked on topological strings, three-dimensional gauge theories. He's the J from ABJM theory. And the last couple of years, he's been mostly active in quantum gravity, and he's going to be telling us about his recent work.
Well, thank you so much for the nice introduction and the chance to visit here. It's always a delight to visit the Simon Center, and this is the first time I've spoken in front of a live audience in quite a long time, so it feels great to be here. So I guess I'm going to give a series of 4 talks over the next 4 days. And so today will serve as kind of an introduction, in a sense, to the things that I'll tell you about. Maybe just to give the references to my own work, that's going to be kind of the thing that I'll focus on, really just pass a few papers of mine. One of them was with Lampro's Lamprou. That one I won't talk about as much this week, but I'll mention it a little bit today. And then and that's about trying to model the experiences of an observer inside of ADS in some controlled way. And then a paper with my student Elliot Schneider, which I'll talk about on not tomorrow, but on Wednesday, which is some attempt to understand more microscopically how this so-called ER equals EPR correspondence works in a string theory context. And then another work with my students David Kaltschmeyer and my former student Ping Gao, who's now a postdoc at MIT. And that one is going to be, that one is about trying to add some new ingredients to this and kind of in an attempt to figure out what it would take to make a theory of 2D gravity into a good theory, in a sense that I'll describe partly today. So I don't know why I wrote this in this order, but this one I'll mention a little bit today, this thing on Tuesday, this on Wednesday, this is sort of today, although it's not the main topic. And then on Thursday, I'll talk about some ideas in progress. So that's kind of the outline from the point of view of those papers, but I'll try to give background and other things. So as I said, today will be mostly an introduction, and I think I'm going to start by motivating it through these black hole information questions. Okay, so sometimes people call it the black hole information paradox, and there are really a bunch of different things that people asked about, unitarity and quantum mechanics in the context of black holes. But I think it's sort of wrong to call it a paradox, because the paradox seems to imply that somebody derived an actual contradiction. But, well, I hope I'll convince you that there really was never any contradiction, but it's an interesting question to pursue, because it might tell us something about how quantum gravity is supposed to work. Okay. And I'll title this section Black Hole Information Questions. Should I write a little bit bigger? Maybe that's too small. Does it seem okay in the back? It's okay? Okay. Okay, and so there are a whole bunch of them, and I'm going to kind of elaborate on them. So I would say the original story from Hawking is the unitarity of black hole evaporation. There's some computation which would seem to indicate that it's not unitary. That seems problematic. And then there was this refinement due to Matur and Amps that was popular some years ago, which is related to this, but has slightly different flavor. And it's a question about the monogamy of entanglement among certain modes in an already mostly evaporated black hole. And then there's another kind of question that we might call the question of escape from the interior. So if I throw something into a black hole and it eventually evaporates, how does it actually causally get out? Is there some way to understand that? That's a more visceral question, maybe. And I have two more things to write. Maybe I'll lift this board up. Now it's going to be too high for me, isn't it? Okay, we'll do it like that. And then, well, another thing which is often not discussed too much, but kind of underlies several of those, and we'll come to it as I get into it a little bit, is what we might call the entropy puzzle. I'll explain what I mean by that when I get to it. Whoops, keep breaking the chalk here. And maybe lastly, and that's related to this paper with Lampro's, what is the experience of the infalling observer? And there's some things that sound a little bit like puzzles there, or at least it's an interesting question. So those are sort of the names. Let me elaborate now on what that means. So what's the original question about unitarity of black hole evaporation? Well, the idea is very simple, so I'm sure everybody knows this, so I'm not going to go into a lot of detail. Just sort of an introduction. Let's suppose we consider a black hole in ADS, just to make our lives simpler, so we don't have to worry about, something from far away in Minkowski space, or in de Sitter space-time. We don't really know how to discuss the Hilbert space. So let's live in ADS. We put our black hole in a box, and if we look at the semi-classical Penrose diagram, let's say there's some matter which collapsed, so some stars sitting here. Then there will be a space-like singularity. There'll be a horizon, and then eventually the black hole will emit Hawking radiation, and it will completely decay away, and we'll end up with a space-time up here that looks like Penrose diagram of black hole evaporation depicted semi-classically. So the black hole region is this chunk in here. And, well, what was the original paradox, so to speak, which is not really a paradox, but anyway, what was the original question? What looks funny in this picture is that you could take a slice, say, at some late time here, and along this spatial slice, it seems that you have a big section of the interior and some section of the exterior. You could evolve the state, the initial state, up to this slice semi-classically. You'll find some pure state. But then, because the black hole finally is completely evaporated, it's tempting to trace over this interior portion. And so the computation that Hawking did, roughly speaking, is to compute the state on this slice. So this is a state on some nice slice at late times. And then in the semi-classical theory of like quantum fields in this background, you could just take the trace over the interior region. So you take this guy and take the partial trace over the Hilbert space of the interior. And of course, this will result in a density matrix, not a pure state for the outside. So that was the Hawking paradox, if you like. And sometimes people think of this, and certainly when Hawking wrote it down, he thought of it as really contradiction between, the low energy effective field theory. So sometimes people discuss this as a contradiction between the IR effective theory of gravity plus matter in this space-time, together with locality and the rules of quantum mechanics, and somehow those three things together lead you to a contradiction. I think that's how Hawking thought this meant. And so that either quantum mechanics is wrong, which is what Hawking originally thought, or locality is wrong, or something else. But really, there was a sneaky step here that didn't just follow from those things, which is that we took this trace over the interior Hilbert space. And taking the trace over the interior Hilbert space would only make sense if the theory that lived here had a Hilbert space which factorizes into regions. So this logic presumes that there is some degrees of freedom here and some degrees of freedom here. In other words, that the total Hilbert space of gravity plus quantum fields in this kind of space-time looks like a tensor product of some exterior Hilbert space and an interior Hilbert space. Well, maybe it's like, I mean, this is supposed to be a kind of bulk semi-classical decomposition. So it's just associated, I mean, this is the Hawking's picture. So it's just associated with quantum fields and perturbatively quantized gravity on this slice, where you think of, this as being one region and this is another region of the spatial slice. I mean, if we want to say it in terms of asymptotic regions, one is this asymptotic region, the other one is, this chunk that dies in the singularity. And the chunk that dies in its singularity is given, in this wrong reasoning, its own factor in the Hilbert space. But that step doesn't, follow from general principles. And in fact, it contradicts semi-classical gravity, because we know that in gravity there's a Gauss law constraint, the diffeomorphism constraint. So in particular, it's not true, even in gauge theory, right? It's not quite true that the Hilbert space factorizes into tensor products in regions, because there may be an overall Gauss law. So that's something we're very familiar with. So this is not true, which is why this step is not correct. And there is no contradiction. You can't really derive a contradiction this way, and that's good, because if you could derive a contradiction, it would mean that something was extremely wrong with one of these ideas, which seems to be very basic idea. So I would say there's never really a paradox, but this line of thinking is very interesting, because it will turn out that in order to make it work is quite subtle. Okay, so the point here is not that there's some contradiction between that's not the point. The point is that in order to actually make this come out correctly and find a unitary evolution requires the UV of the theory to be very special. Okay, so it's not that you can prove that no UV completion can make it work. That would be a contradiction. But rather it's something very special about the UV which will be required to make it work. And I'm going to sort of make that more precise as these lectures go on. So I think that's kind of the way I would understand all of these puzzles, and I'm going to cover the rest of them in a minute. Let me just say a word about this lack of factorization. So we know that in QFT, in gauge theory, we don't have such factorization. So for example, suppose we have an abelian gauge theory on S2, just as a random example, times time. And if we look at the two halves of the S2, you might be tempted to say that the Hilbert space of the whole theory on S2 is a tensor product of the left and the right hemispheres. But we know that's not true because of the Gauss law, right? We can look at the sector on the left half with some charge, total charge little q, and on the right half will also be labeled by some total charge little q, but only the ones where this little q and that little q add up to 0 are allowed in the full Hilbert space, because the whole thing will basically, I'll push this board up in a second, sorry, it sits behind the podium. So the actual story looks like a direct sum over Q of a product like that. And so in particular, that doesn't look like just a simple product of a left and right Hilbert space. Now that sounds like a very basic fact, and you might think that you could try to modify the arguments here and the other ones that I'll come to shortly in order to take this into account. It doesn't really seem like that's such a big deal, right? But somehow in gravity, together with quantum mechanics, the constraint equation has very strong implications. Let me give you an example, a different example, just to illustrate how strong the constraints on the Hilbert space are from the Gauss law in the gravitational case. So let's suppose we were in global ADS. And as some of the thing I'm going to mention here was, well, many people discussed it, but it's discussed very nicely in some works by Suvrat Raju, I should say. But let's say we're in global ADS below the black hole threshold. So we're at low enough energies in global ADS that the configurations look like some particles and fields in various bound states in ADS. No black holes. So in this Hilbert space, if we quantize things, we just studied the theory semi-classically in perturbation theory. We already derived that there's a discrete spectrum. Right, this is, I mean, if you're not familiar with that fact, it's because ADS looks like a confining trap. So if you just look at the modes of a free field in ADS, they have a quantized spectrum, not a continuous spectrum, because they're bound by the ADS potential. And if we include interactions, the spectrum becomes not just an integer space, Fock space, but they're discrete levels. It's not a continuum. Now, because the spectrum is discrete, and we're in a theory that involves gravity, and that's true if we include perturbative gravity, right? That will shift the energy levels around a little bit. There will be the gravitational corrections, but it doesn't change the fact that the levels are not a continuous set of levels. But because we're in gravity, the energy can be measured at infinity, right? So we know that in this low total energy sector of the theory in ADS, the total Hamiltonian is equal to a pure boundary term. We often phrase this of the CFT, the dual CFT that lives on the boundary of T00, but T00 is a component of the metric in the Pfefferman and Graham expansion near the boundary, right? So we don't have to think of this as T of some CFT that we may not know. If we just given the gravity theory, this is just a particular fall off of the metric. In the Pfefferman and Graham expansion of the metric near the ADS boundary, okay? So it's a purely gravitational statement, true perturbation theory. And what does this tell us? Well, it says that if you live near the boundary and you measure the energy, which is just the Gauss law, right? Just measure the flux integral of the gravitational field out at infinity, you will measure the energy. Since the spectrum is discrete, it just nails down the state exactly. So in this example, the Hilbert space is completely not factorized, right? So if you make the measurement near the boundary, it just completely fixes the state in the interior. So it's the opposite from looking like a tensor product of some near boundary degrees of freedom and some interior degrees of freedom. So assuming this kind of factorization is clearly a dangerous step, okay? But in the case where there are black holes, this discussion is more subtle, right? So if we look in perturbation theory around the ADS black hole, then it looks like the spectrum is continuous, okay? And in the ADS black hole, it's not so completely obvious that there's some measurement that you can do at infinity which would totally nail down the state. Okay, so that's not very obvious in perturbation theory. Of course, if we believe ADS CFT, it should be true because in principle, even in the very high energy regime, where the dual looks like a black hole, the spectrum, if ADS CFT is true, is still discrete, although very finely spaced. In principle, if we do some exponentially fine measurement of the ADM energy, we can also nail down the state. So in the full theory, we think it's totally non-factorized. But in this case, it's not obvious in perturbation theory you know, how to use or how important is this non-factorization. Quantum perturbation theory. Yeah. Yeah. We could imagine doing that, yeah. Right, well, here I meant, let's say we'd start with the ADS black hole background, and then we quantize small perturbations around it. We expand around the ADS black hole background, and then the spectrum looks continuous. Whereas we think in the exact theory that the true spectrum, which includes, of course, the black hole as part of the quantum state, is discrete. But it's not obvious how to see that from the point of view of the gravity theory.
Global ADS black hole.
Yeah. This is also a global ADS black hole. Yeah. Right, exactly. Since perturbation theory doesn't distinguish e to the minus s, it's hard to, right. That's right. Yeah, that's right. That's the situation here. Yeah. Okay, so this didn't resolve anything, but it was just meant to. This was just meant to say that there really isn't a sharp. It was never really a sharp puzzle. There's a sharp puzzle only if you assume that there is this factorization, and we know that this factorization is not correct. Now, there's still, I think, a question, which is, how does it actually work, right? But there's no real argument that there was some contradiction between these concepts. Like only if you assume this wrong concept. Yeah, I think so. Yeah, I think that's right. Yeah. Yes. Yeah. Yeah. You mean the eternal black hole? Oh, yeah, sure. Well, maybe those are one of these other puzzles. Okay, so there's a lot list. Some of these are about the eternal black hole, and some of them. So I think that the question about unitarity of the evaporation is for the non-eternal kind of black hole by definition, and then there are some other puzzles which we can ask in the eternal black hole, for example. No, that's true even in a small black hole. If you do perturbation theory around the small black hole, because it has a horizon. So the continuous spectrum. So I guess I didn't write the key point, which I said in words, which is that here it's not obvious because the perturbative spectrum is continuous, and it's continuous whenever you have a horizon. It's just from the existence of the horizon, because then there can be modes that are localized very close to the horizon where the redshift factor goes to 0. So right.
There is no horizon. I throw this up, then horizon gets formed.
Then horizon gets formed, yeah.
Then something happens. Now, you assume there that horizon is forever. That's why entanglement doesn't work.
That's true. I mean, well, okay, but anyway.
Doesn't matter for this question.
I mean, well, I guess it's a chicken and egg question to some extent, but I imagine that the computation is being done here at a certain time, which is before the black hole evaporated. And one studies the quantization of modes on some slice of this type, and then the spectrum will look then the spectrum will look continuous. Of course, later, yeah, I mean, but I think it's not so essential. But yeah. Okay, so then there was this second point about monogamy of entanglement, and the story there was maybe at some level meant to make the Hawking discussion into a sharper paradox, but in a way it still carries the same assumption. So the idea that was the discussion between Matur and Amps is that we just look at the spatial slice near the horizon. Imagine we have some old black hole that's already mostly evaporated. So the picture is, this is a spatial slice. Here's the horizon. And then there's some Hawking quanta very far away that the black hole emitted quite a long time ago. Now they spread out to a big distance. And then we can look at modes of quantum fields in the black hole background near the horizon, just inside and just outside. Now, if unitarity is to be preserved in the evaporation process, if the black hole has already emitted most of the entropy into Hawking radiation, the Hawking radiation that's already emitted should be maximally entangled with the black hole. On the other hand, if the space here is supposed to look locally like the vacuum, this mode should be maximally entangled with this mode, the way it is in the Minkowski vacuum. So it looks like this interior mode I and this exterior mode in H. So it looks like I is supposed to be maximally entangled with both H right, maybe I shouldn't have said maximally. But highly entangled. And you can try to make the amount of this entanglement become very large by picking the correct purification of the mode here in the set of modes here. So it doesn't have to be literally the one like right next to it. It's just that in the Minkowski vacuum, this mode will be entangled with the appropriate combination of these modes, and that will contradict its entanglement with this guy. Okay. Now, but again, this story assumes that there's a factorization of the Hilbert space between these three sectors. So it assumes that these are three separate tensor factors in the Hilbert space, and again, in gravity, it doesn't seem to work like that. So I would say there's no contradiction, again, but it's still somehow a puzzle. How does it actually work, right? So, okay. One way to see how one could get out of this argument, well, the H is supposed to be some already emitted Hawking radiation that's very far away. And E is supposed to be a mode that's very close to the horizon on the outside, which, if this looks like the ordinary, approximately locally flat vacuum state of quantum fields, then this should be highly entangled with this. But if the evaporation process was unitary, then these guys should also have been highly entangled with that, and you can show that it's inconsistent. Inconsistent if this, and this are three separate factors of the Hilbert space. Yeah, sure. If you fall into the black hole, what? Could you say again?
Can you determine if you have passed the horizon? Not only do you know
Well, no. Well, I mean, assuming gravity is approximately correct, then no, as long as the black hole is very large. I mean, you feel tidal forces. Right, exactly. So that seems to be required if you if the horizon looks like a smooth place. And then this entanglement seems to be required by unitarity, and then they would seem to contradict each other. That was the argument of these people. Well, I'm not completely sure if I follow, but so the structure of their argument was, if you assume that the horizon looks like an ordinary place, then these two should be highly entangled, and unitarity should demand that this is highly entangled with that, and then they showed that that's incompatible. And their conclusion was that the horizon was special and you die there in a firewall, but there was an implicit assumption in the whole argument that these three things are separate tensor factors in a Hilbert space, and we saw that in gravity it's not the case that you can split the Hilbert space up by regions, certainly in some situations. So there's no contradiction, but there's just the question of how does the non-factorization make it work, okay? So I think there are interesting questions in these things, but it's not, there's never really a sharp contradiction. Now, so one way to see, in a sense, how this works is through the following sheet. We can imagine that, so what the ingredients in this argument were just that the black hole, this is the black hole interior. So it was just that the black hole was maximally entangled with this already emitted Hawking radiation. So we can make another setup where we have an ADS black hole. Here, yeah, okay. Maybe come over here. Yeah. So let's suppose we have a black hole in global ADS. I'll just draw it with this ADS, and let's imagine that this black hole is maximally entangled with something else. Well, a very simple thing that we could make it maximally entangled with is another copy of the same system. So instead of having it maximally entangled with some radiation, which is a complicated setup, try to get to the heart of the story by entangling it with another ADS black hole, okay? Well, in this setup, I can, okay? So here I doubled the system. So now this looks just like the thermofield double state. So I think of this side as the black hole, and this is some kind of reference system. And since I took a second copy of the whole system, it has its own separate factorized Hilbert space. And then this state looks like the thermofield double state. 1 over the partition function, sum over energies. That's, well, I'm saying maximally entangled, but of course I mean maximally entangled at a given energy or at a given temperature, because of course the total Hilbert space is infinite dimensional. So when I said maximal, I meant fixing the energy of the object. Okay? So this thing is a black hole entangled with some other reference. I agree with you that it really is invalid to say that in the Hawking, if I have a small black hole and it is 90% evaporated, that the black hole is maximally entangled with the radiation is actually an invalid statement because the Hilbert space doesn't factorize. But there's something to understand, because in the sort of most naive or in some semi-classical analysis, it might look like the Hilbert space is factorized. It's somehow a non-trivial thing that it works. And I'm going to describe to you in a lot more detail why it's non-trivial, but also not. It's important, I think, to understand that there's no contradiction, but there's an interesting question whose answer is quite subtle. Okay. So, but this is just kind of some historical background almost. So I wanted to tell people about this for a little bit. So now, quite a long time ago, Juan Aldacena told us what the in the context of ADS-CFT, what the dual of the thermal field double state is supposed to be. It's supposed to be the eternal black hole that Samson was just asking about 15 minutes ago. And so this thing we would describe by this Penrose diagram, where we have the side that I called the black hole side over here, and then this reference side in here, hidden behind the horizon, and we get a Penrose diagram that looks like this. And now we can see that there's no contradiction in this picture, because where are the different pieces of this picture? Well, this mode E is supposed to be a mode on the side that I called black hole here, just outside the horizon. That's the mode over here. The mode I is supposed to be just inside the horizon, so that's over here. And then the Hawking, which was just, I mean, in terms of the actual computation, which are very simple, that was discussed there, the only role, it didn't really matter that this was Hawking radiation, it just mattered that it was maximally entangled with the black hole. Which makes sense, right? You could take the Hawking radiation and read it into some register. We imagine we collected the Hawking radiation and collapsed it into another black hole. But then we apply the duality to the total state, and we get this other picture. So then the system that was called H is this thing, and we see that this mode is contained in this. So there's no contradiction in the mode E being entangled with both I and H, because I is part of H. Okay, so that's sort of an example of how non-factorization can solve this kind of paradox. Okay. Sorry, yeah. E is a mode here, I is a mode over here, and H was the whole system of the right side seen from the outside. So basically I is contained in H. And then then this is not a contradiction, it's obvious, right? Okay. It doesn't answer the unitarity puzzle. Right, well, you know, the unitarity puzzle, I would say just isn't a puzzle. Let's come back. Okay, since you asked that, we'll come back to the unitarity puzzle right now, actually. Let's look at it a little bit more closely. Let's try to follow what the state actually looks like in this evaporation context. Okay, so we started with some. I'm gonna, of course, it's easy to draw space as one-dimensional because the blackboard is only two-dimensional. So, and later I'm going to discuss a lot 2D gravity. So we'll put equations to some of these pictures. But for now, this could be a higher D black hole. But I'm just suppressing all the other directions to draw it. Oh yeah, what? Yeah, I mean, that's because in this picture, I collected this Hawking radiation and I dragged it extremely far away, and I stopped discussing the connection between the two. But we can allow, we can allow there to be a wire that connects these two together. Okay. We could, we could draw these two black holes as being extremely far separated in the same ADS rather than in two different asymptotically ADS regions. Then, of course, we don't have this sharp factorization, but because the distance between them can be arbitrarily large, it shouldn't matter. Okay. I mean, E is supposed to be on the side that, E is supposed to be just outside the horizon of the black hole that we were originally discussing, and I is supposed to be just inside the horizon of that black hole. And then you know, H could have been, you know, we could try to, you know, we could draw a more complicated looking picture, right? I mean, here's the original black hole, and then here's the radiation very far away, and we draw it like a tunnel like this. So here's the radiation, and here is the black hole. And then you discuss some modes just inside and just outside the horizon of this black hole, and then here's the radiation over here. This picture is basically the same as this picture, except that we put the two asymptotic regions together, but with some enormous separation. So this is kind of the limit that we take this separation strictly to infinity. Right? Of course, if the separation becomes extremely far, then the modes E can't really get to H, because it's, you know, a trillion light years away. As in practice, it becomes like that. Yeah, thanks for the question. Okay, but let's go back to the unitarity question. So we, what does the state actually look like? Okay, so let's suppose we had some black hole, maybe we formed from collapse. Let's say that, you know, here's the r equals 0 end of space, here's the asymptotic boundary. Now, but in the Penrose diagram, it kind of hides a little bit what's actually going on inside. So one way to discuss what the state of the space-time containing the black hole is we should work in some gauge. And a very natural gauge to use is maximum volume slice. Basically, spatial slice with the vanishing extrinsic curvature. If we were really in 1+1 dimensions, that would mean that the spatial slice is a geodesic. So we take a point on the boundary, which tells us the boundary time, and then we follow a geodesic, which goes into the interior, and it ends at the r equals 0 origin. And, you know, if it formed from a collapse of some matter, the original matter is, you know, in here. Okay? Okay, so this is supposed to be a geodesic slice, or in higher dimensions. And how do we label these slices? Well, later, it's very soon I'm going to specialize in some case of 2D gravity, where the gravitational variables are very simple. But even in higher dimensions, we could discuss something similar. No, the singularity, well, I mean, this is supposed to be before, I mean, the singularity is in the future. Yeah. This is just the origin of polar coordinates where the center of the star was. Okay? And so one of the things that describes this slice is just the length of this geodesic. And when I say the length, I mean some renormalized length that I could make more precise in a specific example, and I'll do that shortly. Because if we're in asymptotically ADS, of course, there's an infinite length out to the ADS boundary. But we're interested in the length in the interior portion. Now, what actually happens in the evolution? So we have a slice which has some length, and then there's some state of the matter fields living on that slice. That's sort of the semi-classical cartoon. There's a geometry. Over here, I'm just keeping track of the length, and then there's the state of the matter fields. And as this black hole evolves, actually whether it's evaporating or not, the interior gets larger and larger. And so this length basically grows in time proportional to the time as measured from the boundary. Okay, so the black hole interior grows and grows. And at the point when, so sometimes in this context people discuss this so-called page curve. Maybe maybe that's useful for people to see. So if we have our black hole and we let it evaporate out into some other system to try to make the question as sharp as possible, so that we really factorize out the stuff that it evaporates into. So we can take our gravity system and couple it to an external system, and then we can look at what is the amount of entanglement entropy between the external system into which I'm evaporating my black hole and the black hole system. And at first, that entanglement entropy grows until it reaches the original entropy of the black hole, and then it comes down again and goes back to 0. So this is the entanglement entropy. So here I have black hole system coupled to some, at the boundary, coupled to some bath. and I compute the entanglement entropy of those two guys together. This is the time. So first, this entanglement entropy grows because as I evaporate the black hole into the bath, then the state looks, entangled between the black hole and the bath. That entropy grows and grows until it reaches what would have been the entropy of the remaining piece of the black hole, which is about, approximately half of the original black hole entropy. And then it starts to come down again as the black hole fully evaporates, and in the end, the black hole is completely gone. You're back with empty ADS, and everything is in the bath. Then the entanglement entropy is 0 again because you have a pure state in the bath. So this is the curve that one would like to see by unitarity of quantum mechanics. So this is the curve for unitary evolution, in which all of the energy goes from the ADS black hole system into the bath system. But the naive computation just looks like this. Okay, the naive computation looks like this entanglement entropy increases forever and gets bigger than the original entropy of the black hole. It sounds contradictory. That's the reason why if you trace out the interior at some point, you get a mixed state on the outside, because it doesn't look like the quantum information of what was in the black hole came out. It's still inside the black hole, so when you trace over it, you get a mixed state. But we can see it clearly in this simple picture, which I'll discuss in detail in 2D gravity. The length of the interior grows with time. And so, it just says renormalize because of the ADS boundary, but I'll get to that. That's a detail. I'll get to it later. Okay. So the interior grows linearly in time, approximately, at least after the initial transients. And what naive dimensionality of the Hilbert space associated with the bulk theory on these very enormous slices. So this basically looks like a black hole whose interior is enormous, right? So the very late time slice, here's the horizon. And then there's this enormous interior, and then you see the original collapsing matter deep in the interior. But it has this enormous size which is growing in time. And we have to wait here for quite long times, right? Some time scale of order the entropy, which is roughly the evaporation, times some power of the entropy. Depends, some of that depends on the details. If we were in 1+1 dimensions, this time here would be of order the entropy, the initial entropy. And at that point, the interior of the black hole has a size that's about S. So the dimensionality of the Hilbert space of the sort of semi-classical theory looks like a Hilbert space of size e to the s, because the interior has volume s. Okay, so we would sort of estimate the naive bulk computation of the entropy with that it is basically proportional to the length, or it would be some power of the length if we were in higher dimensions, and then this would have another power, and it will work out the same way. Basically proportional to the length, which is proportional to the time t, and that's what this curve is really telling you. So it's not only the entanglement entropy, which looks like it violates the predictions of unitarity, it's just that the total count of the size of the gravity of the bulk Hilbert space violates the Bekenstein-Hawking bound. Okay, so it seems like there can be an enormous number of semi-classical states which look like a black hole with a huge interior. So that's really the origin of all of these puzzles, and the question is, what is it which fixes that? Okay. So we think that in the correct theory, you should not have this enormous entropy of black holes. It's just supposed to be bounded by the horizon entropy. What kills all of these states? Okay.
Space like size is increased.
I can say again? Right. Yes, that's right, but that's some subtle issue. I mean, there's something subtle there because modes that were above the cutoff come down, right? Um, right. Right. I mean, but, well, you know.
Wormholes are born because our universe is expanding.
Well, it's true. That's true. So if our universe was just QFT in a fixed background, then there would not be a contradiction because the theory has infinitely many degrees of freedom, so they just can come from the UV forever. But if our universe looked like a lattice theory, it would be a contradiction, right? Because then you would be adding new lattice sites all the time, and it's explicitly non-unitary, right? Right, but in our universe, it's not a contradiction because of the same subtle effects of gravity. That, in a way, that is related. I mean, that's the same problem in the cosmological context. I would say that's a harder problem to understand. Well, it's not a problem in pure QFT in curved space, but it's a problem if you think that there is a it's a problem if you think that the whole gravitation, the whole system, including gravity, is described by a Hilbert space, right? So the question is, in the expanding cosmology, what is the Hilbert space of the full theory, including gravity? And is it a Hilbert space whose dimensionality is growing? That sounds contradict quantum mechanics, or what, right? In a universe with, well, if we take the global picture in the cosmological case, where we take compact slices, like the spheres that are growing exponentially, I would say the Hilbert space there is one-dimensional. The full Hilbert, the exact Hilbert space is one-dimensional, so it stays one-dimensional forever. And what the rest of it is, I don't know. You know, that's the Hilbert space as seen from the outside. So that situation is much more confusing. Here maybe we could try to understand this question. Right, I mean, in this context too, there's no contradiction if we just live in QFT and curved space, right? The interior grows and grows, and there is this curve, and there's a huge entanglement between the black holes have an enormous entropy because the interior is huge. That's it. There's no contradiction, but it seems to you know.
You only reach a contradiction.
You only reach a contradiction because the black hole is supposed to disappear, right? Right, right. So I mean, so this entropy puzzle means is that the usual QFT in curved space counting violates the Bekenstein-Hawking bound. So which one is right? Okay. Let me see, what time is that? Oh, wow, okay. All right, well, given the time there, let me let's see. Well, I wanted today to start to review a little bit about, so let me tell you, okay, I have sort of, I have like 2 minutes left, so maybe. Okay, well, let me just see what's the best way to organize this 10 minutes. Okay, maybe I'll get to, I'll do that next time. Let me just sort of allude to where I'm going to go, because I don't think I have time to say it in 10 minutes. Doesn't make sense. Oh, is this not this is a bad board to use. Okay, I'll come back over here. Okay, so I want to flesh out some of these ideas in the context of 2D gravity, and I'll review next time some of the basics of 2D gravity. Let me just write sort of what theory I'm going to talk about. So I'm going to spend a while discussing this 2D JT gravity. So it's a very simple theory of gravity in 2 dimensions. It's basically what you will get if you dimensionally reduce down to 2D on a sphere of circles. So if we had pure gravity in 2D, just the metric with the Einstein-Hilbert term. That would have this action, where I also put a boundary of my two-dimensional space. So this M is 2D. But this is a pure topological term. This is just the Gauss-Bonnet integral, so it doesn't lead to any kind of interesting physics. The equation of motion is vacuous, and I either have to make it conformal, as I would on the string worldsheet, or something else, and it doesn't look much like higher D gravity. But the Jakiv-Teitelbaum gravity adds in an additional ingredient, which is some dilaton field, a scalar in 2 dimensions. But that scalar also carries no local dynamical degrees of freedom, but it makes this theory into kind of a better cartoon of higher D gravity. It still has no local, so this is a theory which is 0 degrees of freedom. Yeah. Okay. You mean Liouville or? Yeah, well, I think people like JT gravity exactly because it has no local degrees of freedom. But then we can add matter to it. So we'll also discuss sometimes, and certainly in the context of this discussion of black hole evaporation, we better add some matter, otherwise there's nothing to discuss. But if we add minimally coupled matter, when I say minimally coupled, I mean the matter doesn't couple to the dilaton. That's the curvature to be -2, constant negative curvature, and so there will be no degrees of freedom in the metric variables. If I add some propagating matter, I will have propagating modes in the matter sector. Okay, I don't have time to, I'll discuss next time sort of where this theory kind of came from. But here I just want to make a few basic points. So this theory is nice because in the Lorentzian analysis, it looks UV finite. Okay, so you can construct explicitly the Hamiltonian and Hilbert space of this theory, including matter. So it's a theory which has locally propagating modes, but because the gravity sector is so simple, it basically has the UV features of just the matter part, which are perfectly okay. And so one can really quantize this theory in Lorentz signature exactly. Okay? And in this theory, it just works the way the naive picture works. So we have, we have some kind of space, and it grows roughly linearly in time. And if I have this matter part, it will have an enormous size of the Hilbert space, and nothing will cut it off. Okay? So if I just take this theory in Lorentz signature and quantize it, I would say it's like it has remnants, right? So the black hole never really evaporates. It never goes away. The interior grows to huge size, and there's no contradiction, but it looks like a very different answer than what we think is correct in higher dimensions. One can do something different with this 2D theory, which is that one can analyze it from the point of view of the Euclidean path integral. And this is studied in the case without matter, especially by Sad, Shankford, and Stanford, as well as some other papers. And the Euclidean theory is much richer because you sum over topologies. So the main difference is we sum over some genus. If we want to compute something like the black hole entropy, we have a contribution that looks like the disk. This actually gives the Bekenstein-Hawking-like answer. Well, here it's the kind of, this is supposed to be, here I'm in ADS, not really the plane, but yeah. Yeah, I'm going to go through this more carefully next time. So here I'm just going to sort of, this is a brief summary of what I'm going to discuss next time because we don't have time to do it today. So once you go to the Euclidean theory, you will think that you will compute, for example, the thermal partition function through this disk-like topology. That gives you the Bekenstein-Hawking entropy answer, not the enormous infinite, not divergent answer you will get from this Lorentzian picture. So in this theory of gravity, if we do the usual Euclidean analysis and we do the completely solvable Lorentzian analysis, actually the Euclidean theory is also solvable, this gentleman solved it, they just give discrepant answers. Okay, so this gives a different kind of answer, which looks like it obeys the Bekenstein bound, but it has a different pathology, which is there are contributions where if I have two boundaries, they can be connected by Euclidean wormholes. So this is supposed to be two separate. So this looks like it's a contribution to the square of the partition function, but it's a contribution to the square of the partition function, which is not part of the square of the answer, right? And so in this paper, they interpreted this as some disorder average over a theory. So it basically doesn't give you quantum mechanics, it gives you an average over quantum mechanics. So in this ultra-simplified theory of gravity, both the Lorentzian analysis sort of violates ADS-CFT, and it violates the entropy bound and unitary, On the other hand, the Euclidean analysis doesn't really give you quantum mechanics. It gives you some disorder average over quantum mechanics, and the two answers are also different. And so one of the main things I want to discuss over the next days is sort of like what is required. Let me write this. The question I'll leave you with today. What would be required to get a good theory? A good theory means one where the Lorentzian and Euclidean analysis agree, where the Euclidean analysis wouldn't tell you that you have a disorder average, where the Lorentzian analysis wouldn't give you a violation of the Bekenstein bound. So I think we believe that the correct UV completions of gravity in higher dimensions, the full string theory in ADS5 times S5 is a good theory in that sense. How does that work, right? So it's not, and the point is that even though these black hole questions are not true paradoxes, and that it's not that there cannot be any UV completion which makes it work, you cannot pick a random, this is a bad UV completion of JT. So if we think of JT gravity plus matter as a long distance effective theory, it may not have an intrinsic problem. This is a conjecture for the UV completion, so to speak. It's a very simple UV completion because it turns out this theory is UV complete already. We didn't have to add any degrees of freedom, but it's a bad one in the sense that it doesn't, it leads to a disorder average in the Euclidean analysis, and it leads to a discrepant result in Lorentz signature, which violates the entropy bound. How would it work in a different, can we add something to this theory in the UV so that the Lorentzian and Euclidean analysis agree and it all works? Okay? Well, you could take this point of view. I mean, yeah, okay, that's fine. I mean, sure, this theory is consistent. I would say this theory is perfectly consistent. But I call it a bad theory because, okay, maybe it's semantics, but I don't like this theory, but I mean, it's interesting to study this theory, but okay. Maybe a way to say it is, but by a good theory, I mean one where the Lorentzian and Euclidean analysis give the same answer. Can we find theory of gravity, UV completions of gravity like that? And I think that's what happened. I think that is a feature So first of all, this theory is perfectly consistent, but it's probably not a very good model for string theory in ADS5 times S5, because that does obey the entropy bound, because we know the answer from the CFT side. So although it's a consistent theory, it's a bad model for higher D gravity. So that's what I meant by good. Yeah. I mean, I would say this theory is also consistent, sort of as piece of, I mean, mathematically in some sense. It's a disorder average over quantum systems. That's a consistent structure. I mean, it depends what you take as an axiom, right? But and it's also interesting. But exactly. Yes. Yes.
Show you the picture in a geometric.
Yes. And
now if you try to rewrite that in terms of the quantum mechanics of the it's
right. Yes. No. Well. Okay. Yeah. I'm out of time, and I should say this next time and not now. But since you mentioned that, maybe I'll just let me sketch the cartoon of part of the answer here. Whoops. Can you see it all the way to this one? Oh, yeah. Oh, wow, it's really stuck. Okay. Let me sketch a little bit of the answer. So I'm gonna jump ahead, and we're gonna go over this again next time in a little more detail. Well, you always have to have two boundaries to space. So the simplest thing we can consider is when we have two of the nearly ADS2 boundaries, and then the only variable is the length and its conjugate momentum. And it turns out here that this is in the Lorentzian analysis. The Hamiltonian basically looks like the Liouville quantum mechanics. So very, very simple quantum mechanics. How does this reconcile with the Euclidean analysis? Well, we will say that there is an implicit assumption here, which is that the inner product on these states is the conventional inner product. So when we say that we have a classical system, we describe by this length, and then we quantize it and get this this Liouville potential quantum mechanics, we kind of implicitly assume that the inner product is delta of the length, right? Like when I quantize an oscillator, I assume the inner product in the position basis is the delta function. But how would I compute that inner product using Euclidean methods? I would compute this using Euclidean methods by taking here a thing with length L, here a length L prime. These slices are supposed to be geodesics. So if I don't put any topology in between, then they have to be coincident, and I will get this delta. But if I'm allowed to sum over handles, I can do some funny thing here and put in a bunch of handles, and maybe there's some other garbage, and I get something like that. Yeah. Right, it's a different calculator, but this is sort of the Lorentzian interpretation. Yeah.
What happens there, you are doing something else.
I agree. I agree. I agree. But of course, and that quantum mechanics is fine, and there's no, and it doesn't obey holography, and there's no Bekenstein bound, and it's fine as a quantum mechanics. But the interesting thing is if you modify this quantum mechanics a little bit by saying that we include these kind of things when we discuss the inner product. Okay, if we include these things when we discuss the inner product, then we'll get some corrections here. We can always cut this chunk off like this. So we can write it as an integral of the length of this little cutoff of this gadget, which is a specific constant negative curvature manifold. These are geodesics, and this is a little trumpet. And then here is the sum over all the junk. Okay? Now, if I was in the pure JT gravity without matter, this is a specific answer, which Saad Shankar at Stanford discussed. That came from this work of Mirzakhami. More generally, we might have a theory which is JT-like, but there's some other matter, or maybe there's some branes where the space can end. I'll discuss this at some length. Or some other kind of junk, and maybe I get a different answer here than the pure JT answer. Another computation you could do is to compute the thermal partition function. And that also looks like, well, that looks like the disk. Plus another thing, which is an integral over now this trumpet factor times the sum over all of the junk. So those are sort of, this is the Euclidean computation of the thermal partition function. This is some modification of the Lorentzian theory, which corrects the inner product by gravitational instantons. So this is sort of the gravitational instanton correction to the inner product. Right, and if it turns out, there's a cute identity that I'll tell you next time, that if, suppose that this is a magic function, so imagine, like, that this is equal to a discrete spectrum. Okay, so of course, if I get to pick this at random, I can arrange that this is a discrete spectrum. I don't know what kind of matter I would have to add to achieve that, but at the level of functions, of course, this is just some functional transform. You can find such a function for any choice of spectrum. I'm sure most of those are not physically sensible, but presumably if we took the full string theory, compactified to 2 dimensions, and did this computation, we'll get the function here which makes this a discrete spectrum. If the dual was actually a specific. Then if we plug it in here, we get an answer which agrees in the Lorentzian analysis. How does it work? The way it works is that almost all of these states, there's an infinite number of states here. Most of them become null states. And only the actual spectrum is left over. So if we plug this so a Z which leads to this discrete spectrum will lead in the Hilbert space to all null states based on the structure of this inner product, except energy eigenstates with this same list. So you'll get the same answer. So that's kind of that's sort of a kinematic game. But I think it's an evidence that there could exist theories where it works. Now I don't know what are the ingredients you will add to achieve either of these things, but I think it's an interesting fact that if you achieve, if your theory is such that the Euclidean analysis would give you a discrete spectrum, then if you include those corrections in the inner product, the Lorentzian theory would agree with that. So I think that's kind of a cartoon of how it might work, and over the next couple of days I'll discuss some approaches, but I, of course, will not write any full theory like this, which works. That's probably very hard, but I think that's probably how it's supposed to work. Okay, so I gave it away already today, but all right. I guess that's it. Yeah?